Okay, so back in December of 2025, the world of quantum computing got a massive jolt. A team of scientists down in Australia announced a breakthrough that could, well, fundamentally change the whole race to build a truly useful quantum machine. So let's dive into this.
I mean, that is a huge claim, right? And this wasn't just a press release. This was published in the journal Nature, which is a really big deal. The statement comes from an Australian company called Silicon Quantum Computing, or SQC. And they basically believe they've cracked the single biggest problem that's been holding this entire field back. So what do they do? And why does it matter so much?
To really get why this is such a big deal, we kind of have to back up and remember the incredible promise of this field. What are we even trying to do with these unbelievably powerful and frankly strange new computers?
Well, think about challenges that are just impossible for even the world's fastest supercomputers today. We're talking about designing life-saving drugs by simulating molecules with perfect accuracy, or creating brand new materials from the atom up, or even building an AI that can tackle humanity's biggest problems. That is the quantum promise.
But to unlock all that power, we have to deal with a massive, fundamental problem. And it all starts with the basic building block of a quantum computer, the qubit, and its incredibly fragile nature.
So, the computer you're using right now uses bits. You can think of them like simple light switches. They're either on or off, a 1 or a 0. But a quantum computer uses a qubit, and this is where things get really weird and wonderful. A qubit is more like a spinning coin. While it's up in the air, it's kind of both heads and tails at the same time.
This ability to exist in multiple states at once has a name: superposition. And it's really the source of a qubit's incredible power. It's what allows a quantum computer to explore this huge number of possibilities all at once, instead of just one by one like a normal computer.
And they've got another superpower. It's called entanglement. This is where two qubits become linked, so deeply linked that if you measure one, you instantly know the state of the other, even if it's miles away. Einstein famously called it spooky action at a distance. And it's what allows for these really powerful, coordinated calculations.
But here's the catch. The big villain in our story: errors. Qubits are just unbelievably fragile. I mean, the slightest vibration, a tiny change in temperature, any little bit of background noise can just knock them out of their quantum state and totally destroy the calculation. This is the central challenge for everyone in this field.
So, how do you solve this universal problem of errors? Well, this is where SQC's approach gets really interesting. They decided to build their quantum computer in a radically different way, right down to the individual atom. So all around the world, researchers are taking a few different paths. You've got giants like Google and IBM using these super cold circuits. Other folks are using trapped ions or even particles of light. But SQC, they're carving their own path. They're betting on the one material the tech world knows better than anything else: silicon.
They call it the 14-15 architecture. And the name is actually beautifully simple. They take element 14 from the periodic table, which is silicon, and with just incredible accuracy, they place atoms of element 15, phosphorus, right where they need them to go. And those act as the qubits. We're talking about building something with atomic-level precision. Okay, so this is the crucial point. Why does this atomic-level precision matter so much? How does it actually beat the error problem that plagues everybody else? Well, this is where the results really speak for themselves.
Get ready for this number: 99.99%. That's the fidelity, or accuracy, that SQC achieved in their quantum operations. In a field where every tiny fraction of a percent matters, that is a staggering figure. It represents an incredibly low error rate.
And this is where you can really see the difference. While other systems are struggling with higher error rates that need all this complex correction, SQC's silicon chip has an inherently lower error rate. It's in a class of its own, right out of the box.
So how do they do it? Well, there are a few key reasons. Their qubits, which are built from those phosphorus atoms, are naturally really stable. They can hold their quantum state for a very long time. And crucially, their design is naturally resistant to one of the main types of quantum errors. What that means is they need way less complicated error correction to get a clean result.
And here's the most mind-bending part of all. With most quantum systems, when you add more qubits, you add more noise and more errors. The system actually gets worse as it gets bigger, but with SQC's design, the opposite happens. The system's quality and performance actually improves as it scales. That is a complete and total game changer.
This breakthrough really forces us to rethink the entire competition. For years, we've been asking one question, but
Maybe it's time we started asking a different one. What is the real race for quantum power actually about?
You know, for years, the headlines have all been about the quantity race. Who can build a chip with the most qubits? And look, that's an impressive engineering feat, for sure. But what SQC is proving is that the quality race might be what truly matters. It's not just about having a lot of qubits, it's about having the best, most error-free qubits. And that realization, it could redirect the entire industry. We're talking about changing where investment flows and how we even measure progress.
And here's the bottom line. To build what's called a fault-tolerant quantum computer, that's one that can actually solve those world-changing problems without being drowned in errors, you need a fidelity above 99%. Many systems are still fighting to reach that threshold. SQC is already there.
So this leaves us with a really fascinating question for the future of this entire industry. While some are racing to build bigger and bigger machines, SQC is focused on building with atomic perfection. So, is building the best qubit, not just the most qubits, actually the fastest path to our quantum future?